Hello, friend. Welcome back to another quiet journey through the cosmos. Tonight, somewhere far beyond the edge of what we can see, a star is learning how to die. Not with fire, not with violence, just stillness. It shrinks, it cools, it becomes something smaller than it ever was, yet somehow more patient, more ancient. The universe doesn't mourn it. The universe simply waits. And in that waiting, something beautiful begins. What happens when light learns to rest? What remains when the fire goes out, but the glow refuses to fade? Before we begin drifting into this quiet wonder together, if you find comfort in these soft explorations of the cosmos, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Thank you for being here. Now, let's drift. Tonight we're going to explore one of the universe's most patient secrets, white dwarfs. The quiet remains of dead stars. They don't explode. They don't vanish. They simply become something else entirely. Something dense beyond imagination. Something that remembers what it used to be, even as it slowly forgets how to shine. You don't need to understand everything. Just rest and let curiosity do the listening. Some nights when you look up, you see stars as they are now, bright, burning, alive. But what you're really seeing is light that left those stars years ago, centuries ago, sometimes millennia ago. The star you're watching might already be gone. It might have already collapsed into something quieter, something hidden. A white dwarf doesn't announce itself. It doesn't flare or pulse or beg for attention. It just glows faintly like the last ember of a fire that burned for billions of years. Scientists suggest that our own sun will become a white dwarf one day, not tomorrow, not in your lifetime or your children's or their children's children for countless generations, but in about 5 billion years, when the hydrogen in its core finally runs out, the sun will swell into a red giant shed, its outer layers like old skin, and leave behind a dense, glowing core. That core will be a white dwarf, small, hot, patient. It's strange to think of the sun dying, isn't it? The thing that wakes us every morning, that warms our skin, that makes life possible. One day it will simply stop. But even in stopping, it won't disappear. It will become something quieter. Something that remembers the fire, even when the fire is gone. White dwarfs are made mostly of carbon and oxygen. The same carbon that forms the graphite in your pencil, the same oxygen you breathe, but compressed so tightly that a teaspoon of white dwarf material would weigh as much as an elephant. Gravity crushes the star's remains into something almost unimaginable. Atoms press so close together that electrons themselves begin to resist, creating a strange quantum pressure that holds the star from collapsing further. Scientists call this electron degeneracy pressure. It sounds complicated, but really it's just matter saying, I can't get any smaller, I won't. And so, the white dwarf stays, neither growing nor shrinking, just cooling, slowly, so slowly. Imagine holding a stone that was once molten fresh from a kiln, glowing red hot. You set it down and walk away. When you return hours later, it's cooler, but still warm to the touch. Days later, it's barely warm. Weeks later, it's cold. But the stone remembers the heat. White dwarfs are like that, except the cooling takes not hours or days, but billions of years. They glow not because they're creating new energy, but because they're radiating the energy they once had. Heat from a fire that went out long ago. The first white dwarf ever discovered was found in 1862, though no one knew what it was at the time. Astronomers were studying Sirius, the brightest star in our night sky, when they noticed something strange. Sirius seemed to wobble slightly as if something invisible was pulling on it. Eventually, they found the cause, a faint companion star orbiting Sirius. They called it Sirius B. Sirius B is tiny compared to Sirius A, but it's incredibly dense. When scientists finally measured its mass, they were shocked. This small, dim star weighed almost as much as our sun. How could something so small be so heavy? It didn't make sense. Not with the physics they understood at the time. It took decades to figure out. Sirius B wasn't a normal star. It was a white dwarf, a star that had already died, already shed its outer layers, already collapsed into something far denser than anything they had imagined. It was the first glimpse humanity had into the strange, patient afterlife of stars. And Sirius B is still there, still orbiting its bright companion, still glowing faintly, still cooling, still waiting. Here's something most people get wrong about white dwarfs. They assume all stars become white dwarfs. They don't. Only stars with a certain mass, roughly between half the mass of our sun and about 8 times our sun's mass, end their lives this way. Stars much larger than that don't have the luxury of a quiet death. They explode. Supernovae, neutron stars, black holes. The universe reserves the gentle fade for the ones in the middle, the ones like our sun. It's almost poetic, isn't it? The middle-sized stars, the unremarkable ones, the ones that don't burn too bright or too fast, they're the ones that get to rest. The giants burn out violently, the small ones barely flicker. But the in-between stars, the patient ones, they get to become something lasting, something quiet. Think about that. In the vastness of space with all its chaos and light and endless motion, there are places where things slow down, where stars stop burning and start remembering, where gravity holds them gently, like a hand cupping the last warmth of a dying flame. White dwarfs don't die quickly. They can't. There's no process left to speed things along. No fusion, no collapse, no explosion. Just time, just entropy. Just the slow, inevitable evening of temperature. Some white dwarfs we observe today are still hotter than 100,000 Kelvin, about 17 times hotter than the surface of our sun. But they're cooling. In 1 trillion years, they'll be cooler still. In 10 trillion years, they'll be almost dark. Almost. But here's the astonishing part. The universe isn't old enough yet for any white dwarf to have gone completely cold. Not a single one. Every white dwarf in existence, no matter how old, still has some faint glow left. Still carries some remnant of the fire it used to be. The universe is only about 13.8 billion years old. White dwarfs can take quadrillions of years to cool completely. We're not even close. So, when you think about white dwarfs, you're not thinking about death. Not really. You're thinking about memory, about persistence, about the way things linger even when they seem to be gone. There's a white dwarf about 40 light-years from Earth called von Maenen's star, named after the Dutch-American astronomer who discovered it in 1917. It's one of the closest white dwarfs to us. And like Sirius B, it's faint, so faint you'd never see it without a telescope. But it's there, glowing softly, cooling slowly, drifting through space like a memory the universe refuses to let go of. Scientists have studied Van Maenen's star for over a century now, watching how it moves, measuring its light, calculating its temperature. And every measurement confirms the same quiet truth: it's dying, but it's taking its time. No rush, no urgency. Just the patient passage of cosmic time. That's what white dwarfs teach us if we're willing to listen. They teach us that endings don't have to be violent, that light doesn't need fire to exist, that even when the source of energy is gone, the warmth can linger for eons. They teach us patience on a scale we can barely comprehend. Do you ever wonder what it would be like to stand on the surface of a white dwarf? Of course you couldn't. Gravity would crush you instantly. But imagine just for a moment if you could. The sky would be strange. No atmosphere to scatter light, so the stars wouldn't twinkle. They'd be sharp, precise points of light against the blackness. And beneath your feet, if you had feet, the ground would be hot, searingly hot, glowing faintly in the darkness. You'd be standing on a ball of compressed carbon and oxygen, a crystallized memory of a star that once burned bright enough to light entire solar systems. It's hard to imagine something so dense, so patient, so quiet. But that's the beauty of white dwarfs. They don't ask to be understood. They just exist. Cooling, waiting, remembering. And here's a question worth pondering. As you drift towards sleep tonight, if our sun will one day become a white dwarf, what will the night sky look like? Then, there will be no Earth, of course, not as we know it. When the sun swells into a red giant, it will likely consume the inner planets. But if somehow something survived, if some distant observer could watch from afar, they'd see a tiny glowing ember where our sun used to be. A white dwarf no bigger than Earth, but containing almost all the mass the sun ever had. Still warm, still glowing, still there. The universe has a way of holding on to things, even stars. Before we move forward, let this settle in. Your mind, white dwarfs are not endings. They are transitions. They are the in-between. The place where fire becomes memory, where mass becomes patience, where light learns to exist without burning. And that transition, that slow cooling, that quiet glow, it's happening right now all across the universe. In every galaxy, in every corner of space, stars are finishing their lives and becoming something softer, something smaller, something that will outlast nearly everything else. So, when you think of white dwarfs, think of them not as corpses, but as monuments. Monuments to time, to gravity, to the strange and beautiful way the universe refuses to let anything truly disappear. The next time you look up at the night sky, remember some of those stars are already gone. Already white dwarfs, already glowing on borrowed light, on ancient heat, on memory alone. And they'll keep glowing faintly, patiently, long after we're gone, long after everything we know is gone. That's the quiet power of a white dwarf. It doesn't burn. It doesn't shout. It simply endures. But to understand how a star becomes a white dwarf, we need to step back. We need to see the life that came before the stillness. We need to watch how stars burn, how they swell, how they shed their outer layers like old skin, leaving behind only the core, only the memory. Let's drift back to the beginning, to when stars were young and full of fire. Every star begins the same way. A cloud of gas and dust drifting quietly through space, minding its own business. Then gravity whispers. The cloud begins to collapse, slowly at first, then faster. The center grows hot. Atoms collide. Pressure builds. And suddenly, somewhere deep inside that collapsing cloud, hydrogen atoms fuse into helium. Light erupts. A star is born. For billions of years, that star will burn, steady, reliable, balanced. Fusion in the core pushes outward. Gravity pulls inward. The two forces hold each other in perfect tension, like a breath held just long enough to feel calm. Scientists call this the main sequence phase. It's the longest, quietest chapter of a star's life. Our sun has been in this phase for about 4.6 billion years. It will stay here for another 5 billion more. But nothing lasts forever, not even stars. The hydrogen in a star's core is fuel, and like any fuel, it runs out. When that happens, the balance breaks. Fusion slows. The outward pressure weakens. Gravity, patient as always, begins to win. The core contracts. And as it contracts, it heats up. The star, sensing its own decline, does something desperate. It swells. This is the red giant phase. The outer layers of the star expand outward, sometimes growing hundreds of times larger than they were before. The surface cools, turning from white hot to red. But inside, the core burns hotter than ever, hot enough to fuse helium into carbon and oxygen, hot enough to hold off the collapse a little longer. Research shows that when our sun becomes a red giant, it will engulf Mercury, maybe Venus, possibly even Earth. The oceans will boil away. The atmosphere will strip into space. Everything we've ever known, everything we've ever built, will dissolve into the expanding shell of a dying star. But the sun won't notice. It will just keep swelling, keep burning, keep trying to survive. Red giants are beautiful in a strange way. They glow softly like embers. They're so large that if you placed one where our sun is now, its surface might stretch past the orbit of Mars. Imagine standing on a distant moon and watching your star grow so large it fills half the sky. Imagine the light turning from bright yellow to deep glowing red. Imagine knowing that this is the beginning of the end. One of the most famous red giants in our night sky is Betelgeuse, the bright red star in the constellation Orion. Betelgeuse is massive, about 700 times the diameter of our sun. If you placed it at the center of our solar system, it would swallow everything out to Jupiter. Scientists believe Betelgeuse is near the end of its life. It could explode as a supernova anytime in the next 100,000 years. Or it could have already exploded, and the light just hasn't reached us yet. But Betelgeuse won't become a white dwarf. It's too massive. Stars like Betelgeuse end violently collapsing into neutron stars or black holes. White dwarfs are reserved for the smaller, quieter stars, the ones like our sun. Here's where most people misunderstand stellar death. They think all stars explode. They think death in space is always dramatic, fire and noise and shock waves tearing through the cosmos. But that's not true. Most stars die quietly. They shed their outer layers gently like leaves falling from a tree in autumn. What's left behind is just the core. Small, dense, hot, a white dwarf. The process is called a planetary nebula, though it has nothing to do with planets. When a red giant finally exhausts its fuel, it can no longer hold its outer layers. The shell of gas drifts away, blown outward by radiation and stellar winds. For a few thousand years, that shell glows lit from within by the hot core left behind. It looks like a bubble, a ring, a delicate sphere of light expanding into the darkness. The Ring Nebula, located in the constellation, Lyra, is one of the most studied planetary nebulae. It's about 2,000 light-years away. Through a telescope, it looks like a perfect smoke ring floating in space, glowing faintly green and blue. At the center of that ring is a white dwarf, no larger than Earth, but still hot enough to make the surrounding gas shine. Scientists suggest the Ring Nebula formed about 4,000 years ago. That means when ancient civilizations were building pyramids and writing the first epics somewhere far away, a star was dying. It shed its skin. It left behind a glowing shell, and at its heart, a white dwarf was born. Another stunning example is the Helix Nebula, sometimes called the Eye of God. It's one of the closest planetary nebulae to Earth, only about 700 light-years away. When you look at images of the Helix Nebula, you see layers, shells within, shells colors bleeding from red to blue to violet. And at the very center, almost hidden in the light, is a tiny white dwarf, the remnant, the memory, the quiet core of a star that once burned bright enough to warm distant worlds. Planetary nebulae don't last long. A few tens of thousands of years, maybe. Then the gas disperses, the shell fades, the nebula dissolves back into the interstellar medium, recycling its material for future stars, future planets, future life. But the white dwarf remains. It doesn't fade, it doesn't dissolve, it just cools, slowly, patiently, alone. Here's something that surprises people. The creation of a white dwarf isn't instantaneous. It's not like flipping a switch. When the red giant sheds its outer layers, the core doesn't immediately become a white dwarf. It's still surrounded by thin wisps of gas. It's still radiating energy. It takes time for the remaining material to settle, for the core to stabilize, for the white dwarf to truly emerge. During this transition, the core is incredibly hot, sometimes over 100,000 Kelvin. That's about 18 times hotter than the surface of our sun. The ultraviolet radiation from the core ionizes the surrounding gas, making it glow. That's what we see as a planetary nebula. The white dwarf itself is too small, too faint to see clearly, but its energy lights up everything around it. There's a common mistake people make when they think about red giants and white dwarfs. They assume the red giant is the dying star, and the white dwarf is something new. But that's not quite right. The white dwarf is the red giant. It's the same star, just stripped down to its essence. Everything else, the outer layers, the glowing shell, the planetary nebula, was always temporary. The core was always there, burning quietly at the center, waiting to be revealed. Think of it like this. Imagine a candle burning down. The flame is bright, the wax melts and drips away. Eventually, all that's left is a tiny stub still warm, still glowing faintly in the darkness. The flame is gone, but the heat remains. That's what a white dwarf is, the stub of a star, the part that refuses to go out completely. The lesson here is subtle but profound. In the universe, transformation is inevitable. Stars don't stay the same. They burn, they swell, they shed, they shrink. But through all of that change, something essential remains. The core, the center, the part that holds on when everything else lets go. When our sun dies, it will follow this same path. It will swell into a red giant. It will fuse helium into carbon and oxygen. It will blow away its outer layers, creating a planetary nebula that future observers, if there are any, might name and study and wonder about. And at the center of that nebula will be a white dwarf, a tiny glowing ember no bigger than Earth, containing almost all the mass the sun ever had. That white dwarf will be hot at first. It will radiate energy into the void, lighting up the gas around it for a few thousand years. Then the gas will fade. The nebula will dissolve, and the white dwarf will be left alone, cooling in the silence. But here's the beautiful part. Even then, it won't be gone. It will still be there, still glowing, still holding the memory of everything it used to be. The planets it once warmed, the light it once gave, the life it once made possible. Scientists have found thousands of planetary nebulae in our galaxy. Each one marks the site of a star's death. Each one contains at its heart a white dwarf. Some are young, still hot, still bright. Others are older, cooler, harder to see. But they're all there, all waiting, all slowly fading into the background hum of the cosmos. One of the oldest known white dwarfs in our galaxy is WD 0346e plus 246, located about 170 light-years from Earth. It's roughly 11 billion years old, almost as old as the universe itself. It's one of the coolest white dwarfs ever discovered, with a surface temperature of only about 3,900 Kelvin. That's cooler than some red dwarfs. It's so faint that astronomers had to search for years to find it. WD 0346 plus 246 is a glimpse into the deep future. It's what all white dwarfs will eventually become. Cool, dim, nearly invisible, but still there, still real, still a monument to a star that burned billions of years ago. Do you ever think about how long that is? 11 billion years? The sun hasn't even existed that long. Humans have only been around for a few 100,000 years. Civilization for a few thousand. And yet, this white dwarf has been cooling quietly, patiently, for longer than almost anything else in the galaxy. That's the power of patience. That's the power of persistence. White dwarfs don't rush. They don't hurry. They just exist. And in existing, they outlast nearly everything. As we drift deeper into this story, remember white dwarfs are not born from violence. They're born from release, from letting go, from the slow, inevitable shedding of everything that was temporary, leaving only what was always meant to remain. The red giant swells, the outer layers drift away, the core is revealed, and in that revelation, something quiet and beautiful emerges, something that will glow softly in the darkness for trillions of years to come. But what keeps that core from collapsing completely? What stops it from crushing itself into oblivion under its own weight? That's where the physics gets strange. That's where quantum mechanics steps in and says, not yet, not like this. Let's see what happens when gravity meets the limits of matter itself. There's a moment in the life of every dying star when everything hangs in balance. The outer layers have drifted away. The planetary nebula glows softly in the distance. And at the center, the exposed core begins to collapse. Gravity pulls inward, relentless, patient, unstoppable. The core shrinks. Atoms are crushed closer together, closer still. And then something strange happens. Something that defies everything we think we know about matter. The collapse stops, not because of heat, not because of fusion, but because of something far more fundamental, something written into the fabric of reality itself. A quantum rule that says matter can only compress so far. Beyond that, the universe says no. This is the moment a white dwarf is born, not in fire, not in explosion, but in resistance, in refusal, in the quiet defiance of particles that cannot be squeezed any further. Gravity is one of the most patient forces in the universe. It doesn't rush, it doesn't demand. It just pulls, always pulling. In a normal star, fusion pushes back. The heat and pressure from nuclear reactions create an outward force that balances gravity's inward pull. But when fusion stops, when the fuel runs out, there's nothing left to push. Gravity wins. The core collapses. As the core shrinks, something astonishing happens. The density increases, not gradually but dramatically. A cubic centimeter of white dwarf material can weigh as much as a car. A teaspoon can weigh as much as an elephant. A sugar cube can weigh as much as a mountain. The atoms are pressed so tightly together that the space between them almost disappears. In normal matter, atoms are mostly empty space. The nucleus sits at the center, tiny and dense, while electrons orbit far away in probability clouds. But in a white dwarf, that space collapses. The electrons are stripped from their atoms and packed so closely together that they form what scientists call a degenerate electron gas. It sounds abstract, but it's beautifully simple. It's just electrons crowded so tightly that they can't move freely anymore. And here's where quantum mechanics steps in. There's a principle in physics called the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. It states that no two electrons can occupy the same quantum state at the same time. It's a rule, not a suggestion, a fundamental law of nature. And when electrons in a white dwarf are packed together, this principle creates a pressure. Not a thermal pressure, not a pressure from heat, but a quantum pressure. A pressure that arises simply from the fact that electrons refuse to be in the same place. Scientists call this electron degeneracy pressure. It's what holds a white dwarf up. It's what stops the collapse, not heat, not fusion. Just the stubbornness of electrons following the rules of quantum mechanics. Think about that for a moment. A white dwarf the size of Earth containing the mass of the sun, held up not by fire or energy, but by a quantum principle, by the refusal of tiny particles to overlap. It's almost poetic. The universe at its smallest scale has rules, and those rules invisibly silently hold up the remnants of dead stars. But there's a limit. There's always a limit. In 1930, a young Indian physicist named Subramanian Chandrasekhar was traveling by ship from India to England to begin his studies at Cambridge. He was 19 years old. During that long voyage, he spent his time working through calculations, exploring what would happen to a star as it collapsed. He wanted to know, could electron degeneracy pressure hold up a star of any mass? Or was there a breaking point? What he discovered changed astrophysics forever. He found that there is a maximum mass a white dwarf can have. Beyond that mass, electron degeneracy pressure isn't strong enough. Gravity wins. The star collapses further past the white dwarf stage into something even stranger, a neutron star, or a black hole. That maximum mass is called the Chandrasekhar limit. It's approximately 1.4 times the mass of our sun. Any white dwarf heavier than that cannot exist. It will collapse. It has no choice. When Chandrasekhar presented his findings, the scientific community didn't believe him. Some of the greatest astronomers of the time dismissed his work. They thought he'd made a mistake. How could there be a limit? How could the universe simply refuse to allow something to exist? But Chandrasekhar was right. Decades later, observations confirmed it. Every white dwarf ever discovered has a mass below the Chandrasekhar limit. Not one exceeds it. The universe, it seems, follows its own rules. Chandrasekhar eventually won the Nobel Prize in Physics in 1983 for this work, but it took more than 50 years. 50 years for the world to catch up to what a 19-year-old figured out on a ship in the middle of the ocean. Here's a common mistake people make. They assume white dwarfs are cold because they're dead. But that's not true. White dwarfs are hot, incredibly hot. When a white dwarf first forms, its surface temperature can exceed 100,000 Kelvin. That's nearly 20 times hotter than the surface of our sun. The reason white dwarfs glow isn't because they're creating new energy. They're not fusing anything. They're just radiating the residual heat from their past. Heat left over from billions of years of fusion. Heat that will take trillions of years to dissipate. Imagine a coal pulled from a fire and placed on a stone. The coal glows red, then orange, then dim. But even when it looks dark, if you touch it, it's still warm. That warmth can last for hours. White dwarfs are like that coal, except their warmth lasts for eons. One of the most extreme white dwarfs ever observed is called REJ0317853. It's one of the hottest white dwarfs known, with a surface temperature of around 170,000 Kelvin. It's located about 50 light years from Earth. If you could somehow see it with your eyes, it would glow an intense blue-white, almost painful to look at. But it's tiny, only about the size of Earth. All that heat, all that energy compressed into something so small, you could almost hold it in your imagination. REJ0317853 is young, cosmically speaking. It hasn't had time to cool yet, but it will. In 1,000,000 years, it will be cooler. In 1,000,000,000 years, cooler still. In 1,000,000,000,000 years, it will be a faint, dim ember drifting through the void. But even then, it will still exist, still held up by electron degeneracy pressure, still defying gravity, still refusing to collapse. The density of a white dwarf is almost impossible to comprehend. If you could somehow take a piece of white dwarf material the size of a marble and bring it to Earth, it would weigh about as much as a large truck. If you dropped it, it would fall straight through the ground, through the crust, through the mantle, sinking toward the Earth's core, not because it's trying to, but because nothing could support its weight. Some people wonder what would happen if you stood on a white dwarf. The answer is simple. You couldn't. Gravity on the surface of a white dwarf is roughly 350,000 times stronger than gravity on Earth. You would be flattened instantly, crushed into a layer of atoms, not even atoms, just particles pressed into the surface, indistinguishable from the star itself. But let's imagine just for a moment that you could observe a white dwarf from a safe distance. What would you see? You'd see a small sphere glowing faintly. No atmosphere, no weather, no movement. Just a smooth, hot surface radiating light into the void. The sky above it would be filled with stars, sharp and clear, because there's no air to blur them. And beneath that surface, packed into the core, would be carbon and oxygen atoms pressed so tightly together that they're almost a solid. Scientists believe that as white dwarfs age and cool, their cores begin to crystallize. The carbon and oxygen atoms, no longer moving rapidly from heat, settle into a lattice structure. They form crystals, not like the crystals you see in rocks or jewelry, but crystals nonetheless, structures, order, patterns emerging from chaos. In 2019, astronomers confirmed this prediction by studying a group of white dwarfs in our galaxy. They noticed that some white dwarfs were cooling more slowly than expected. The reason they concluded was crystallization. As the core crystallizes, it releases latent heat, similar to how water releases heat when it freezes. That extra heat slows the cooling process. It means that some white dwarfs are slightly warmer, slightly brighter than they would otherwise be. This discovery was profound. It meant that inside some white dwarfs there are actual crystals, giant planet-sized diamonds and oxygen lattices hidden beneath layers of degenerate matter cooling slowly in the darkness. The universe, it seems, has a way of creating beauty, even in death. But the Chandrasekhar limit is always there waiting. If a white dwarf ever gains mass, if it pulls material from a companion star, or if it merges with another white dwarf, it can approach that limit. And if it crosses 1.4 solar masses, electron degeneracy pressure fails. The star can no longer hold itself up. Gravity takes over. The collapse continues. And in that collapse, something violent happens. The star explodes. A Type Ia supernova. A flash of light so bright it can outshine entire galaxies. But that's a story for later. For now, let's rest in the knowledge that most white dwarfs never reach that limit. Most of them are safe, stable, held up by the invisible pressure of electrons refusing to overlap, held up by quantum rules written into the foundation of reality. There's a lesson in that, if you're willing to see it. Even when everything seems to collapse, even when gravity pulls and pressure fades and the fire goes out, there are still rules, still limits, still invisible forces holding things together. Not because they want to, not because they care, but because that's how the universe works. Some things just don't collapse. Some things just endure. White dwarfs teach us about limits, about the boundaries of matter, about the moment when physics says this far and no further. They teach us that density has a meaning, that mass has consequences, that the universe for all its chaos follows laws. And in following those laws, white dwarfs exist. Small, dense, patient, cooling slowly in the void. Monuments to the moment when gravity met quantum mechanics and quantum mechanics won. But even as they cool, they still glow. Even as they fade, they still shine. And that glow, faint as it is, carries a story of collapse and resistance, of death and persistence, of light that lingers long after the fire has gone. So, what does that light look like? What does it mean for something to glow without burning? Let's drift into that question and see where it leads. There's something deeply strange about light that comes from memory, not from burning, not from creation, just from the slow release of heat that was stored long ago. A white dwarf doesn't make light the way our sun does. It doesn't fuse hydrogen into helium. It doesn't ignite anything. It just glows, like a stone pulled from a fire still warm hours later, like the fading heat of a day that's already ended. This is light without fire, radiance without fuel, a glow that asks nothing of the universe except time, and time, patient as always, gives it freely. Imagine holding your hand near something warm. You feel the heat radiating outward even though there's no flame. That's thermal radiation. Energy moving from hot to cold, slowly inevitably following the laws of thermodynamics. White dwarfs work the same way. They're hot, incredibly hot. But that heat is finite. It's not being replenished. Every photon that escapes into space carries away a tiny fraction of the star's remaining energy. And with each photon, the white dwarf cools. Just a little, just enough. Research shows that a white dwarf can take billions of years to cool from 100,000 Kelvin to 10,000 Kelvin, and then billions more to cool from 10,000 to 5,000. The process slows as the temperature drops. The cooler it gets, the slower it cools. It's an asymptotic curve approaching zero, but never quite reaching it. Not in any time frame we can imagine, not in the current age of the universe. When a white dwarf first forms stripped bare from its red giant shell, it's blazingly hot. The surface can reach temperatures of 150,000 Kelvin or more. At that temperature, it glows blue-white, almost ultraviolet. If you could see it with human eyes, it would be painful to look at. A tiny point of searing light, no bigger than Earth, radiating with an intensity that defies its size. But it's not creating that light. It's just remembering it. Remembering the billions of years it spent fusing hydrogen. Remembering the heat generated in its core during the long, stable burn of the main sequence. Remembering the helium fusion of its red giant phase. All of that energy, all of that history, compressed into the core, and now slowly leaking out into the void. One of the nearest white dwarfs to Earth is Sirius B, the companion to Sirius, the brightest star in our night sky. Sirius B is about 8.6 light-years away. It orbits Sirius A every 50 years in a slow elliptical dance. Sirius B has a surface temperature of around 25,000 Kelvin, which makes it hotter than our sun, even though it's much smaller and far dimmer. Here's what's fascinating. Sirius B is only about 12,000 kilometers in diameter, roughly the size of Earth. But it contains about 98% the mass of our sun. All of that mass, all of that matter, packed into something you could almost fit between New York and Los Angeles. And it glows. Not because it's alive, not because it's burning, but because it's still warm from a fire that went out thousands of years ago. When astronomers first discovered Sirius B in 1862, they had no idea what they were looking at. They saw a faint star orbiting Sirius, but its brightness didn't match its mass. It was too dim for something so heavy. It took decades to understand. Sirius B wasn't a normal star. It was something new, something strange, a white dwarf. In 1915, astronomer Walter Sidney Adams measured the spectrum of Sirius B and confirmed what others had suspected: it was white-hot but incredibly small. The implications were staggering. If something that small could be that hot, it had to be unimaginably dense. The physics of the time couldn't explain it. Not yet. Not until quantum mechanics came along and revealed the secret electron degeneracy pressure. Sirius B is still there, still glowing, still orbiting its bright companion. It will continue to glow for billions of years, slowly cooling, slowly fading, but never quite going dark. There's a common misunderstanding about white dwarfs and light. People assume that because they're dead, they must be dim. But that's not always true. Young white dwarfs are bright, shockingly bright for their size. They can outshine red dwarfs and even some main sequence stars. It's only over vast stretches of time that they dim. And even then, they don't disappear. They just become harder to see. Think about the colors of white dwarfs. When they're young and hot, they glow blue or white. As they cool, they shift to yellow, then orange, then red. Eventually, after trillions of years, they'll be so cool they'll glow infrared, invisible to the human eye, but still radiating faintly in wavelengths we can't see. Some scientists call these hypothetical objects black dwarfs, though none exist yet. The universe simply isn't old enough. The oldest white dwarfs we've detected are around 11 to 12 billion years old, nearly as old as the galaxy itself. They've been cooling for almost the entire history of the Milky Way, and yet they still glow, faintly, dimly, but measurably. They haven't gone dark, they haven't stopped. They're still radiating, still giving off the last whispers of heat from stars that died when the universe was young. One such ancient white dwarf is WD 0346Plo-246, located about 170 light-years from Earth. It's one of the coolest white dwarfs known, with a surface temperature of roughly 3,900 Kelvin. That's cooler than many red dwarfs. It's so dim that it's almost invisible even with powerful telescopes. But it's there, a relic, a fossil, a memory of a star that burned and died long before our sun was born. Scientists study white dwarfs like WD 0346Plo-246 to understand the history of our galaxy. Because white dwarfs cool at a predictable rate, they act as cosmic clocks. By measuring their temperature and brightness, astronomers can estimate how long they've been cooling. And from that, they can infer the age of the stellar populations around them. White dwarfs, in a sense, are time capsules. They carry the history of the galaxy in their glow. Here's something most people don't realize: the light from a white dwarf isn't just thermal radiation. It's also a spectrum, a fingerprint. By analyzing the wavelengths of light a white dwarf emits, scientists can determine what it's made of. Most white dwarfs are composed primarily of carbon and oxygen, the leftover products of helium fusion. But some contain traces of other elements: magnesium, neon, even iron. These elements tell a story. They reveal what the star fused during its life, what it created, what it left behind. In 1995, astronomers discovered a white dwarf called GD 362, located about 150 light-years away. Its spectrum was unusual. It showed signs of heavy elements, calcium, magnesium, iron elements that shouldn't be on the surface of a white dwarf. The surface should be pure hydrogen or helium, the lightest elements that float to the top. So, where did the heavy elements come from? The answer scientists concluded was pollution. GD 362 had consumed something, a planet, an asteroid, a rocky body that strayed too close and was torn apart by the white dwarf's gravity. The debris fell onto the surface, contaminating the star's atmosphere with heavier elements. It was evidence of a planetary system long dead, being slowly devoured by the remnant of its own star. This discovery changed how we think about white dwarfs. They're not just passive remnants. They're active participants in the final act of their solar systems. Planets, moons, asteroids, anything that survives the red giant phase might eventually spiral inward and meet its end in the white dwarf's gravity well. Imagine that. A planet that once orbited a living star, perhaps with oceans and atmospheres, now shattered into dust and falling onto the glowing corpse of its sun. The white dwarf absorbs the debris, and for a brief time, those heavy elements appear in its spectrum, a faint trace, a whisper, a reminder that something once existed there. This process is happening all over the galaxy. White dwarfs are eating the remains of their planets, and in doing so, they're telling us about worlds that no longer exist, worlds we'll never see, worlds that are now just lines in a spectrum detected by telescopes, analyzed by computers, and pondered by scientists trying to piece together the story. There's a poetic symmetry in that. The star gave life to its planets. It warmed them with its light, and now, at the end, the planets give themselves back to the star. Not in violence, not in fire, just in slow decay, orbits degrading, distances closing, until finally they fall. But even without planets to consume white dwarfs' glow, they don't need fuel, they don't need company, they just need time. Time to radiate, time to cool, time to fade into the background hum of the cosmos. And that glow, faint as it becomes, is still light. Still photons traveling through space, carrying energy, carrying information, carrying the memory of a star that once burned bright enough to create worlds. Do you ever wonder what it would be like to live near a white dwarf? Of course you couldn't. Not really. There would be no warmth, no life-giving light. But if somehow a planet survived, if somehow it orbited at just the right distance, what would the sky look like? The white dwarf would appear small in the sky, tiny, a pinprick of light, but intensely bright for its size. Depending on its temperature, it might glow blue or white or pale yellow. It wouldn't rise and set dramatically like our sun. It would just hang there, steady, unchanging, providing a faint, constant illumination. The nights would be strange. Other stars would be visible even during the day because the white dwarf's light wouldn't scatter in an atmosphere the way our sun's does. The sky might be filled with stars, always a perpetual twilight, where day and night blur together. But slowly, over millions and billions of years, the white dwarf would dim. The sky would darken. The faint warmth would fade. And eventually, that hypothetical planet would drift through space in near total darkness, lit only by the distant stars orbiting a cold ember that no longer gives anything but gravity. That's the fate of white dwarfs. Not dramatic, not sudden, just slow, inevitable cooling. A fade so gradual you'd never notice it in a human lifetime, or 1,000 human lifetimes, or 1,000,000. Scientists estimate that it takes about 10 billion years for a white dwarf to cool from its initial 100,000 Kelvin down to around 5,000 Kelvin, roughly the temperature of a red dwarf. After that, the cooling slows even more. It could take another 100 billion years to cool to 1,000 Kelvin. And even then, it wouldn't be completely cold. it would still radiate faintly and the infrared still detectable, still real. There's a lesson in that patience, in that slow, relentless dimming. White dwarfs don't rush. They don't hurry toward oblivion. They take their time. They exist in a state of almost but not quite glowing, faintly in the void, refusing to disappear completely. And perhaps that's the most beautiful thing about them. They remind us that endings don't have to be abrupt, that light doesn't need to be bright to matter, that even the faintest glow, the smallest warmth can persist for eons if given enough time. White dwarfs are patient teachers. They teach us that energy once created doesn't vanish. It transforms, it spreads. It radiates away into the universe photon by photon until there's almost nothing left. Almost. But never quite nothing. And almost in that faint persistence, there's a strange kind of hope. A reminder that even when the fire is gone, even when the fuel is spent, something remains. Something that glows, something that endures. But what happens when that glow becomes something more? When the elements inside begin to settle, to organize, to crystallize? That's when white dwarfs reveal one of their most astonishing secrets. Deep inside a white dwarf, beneath layers of degenerate matter, beneath the glowing surface, something remarkable begins to happen. The atoms slow down, the heat fades just enough, and carbon and oxygen, the elements forged in the heart of a dying star, begin to arrange themselves. Not randomly, not chaotically, but in patterns, in structures, in crystals. The core of a white dwarf, scientists now believe, can crystallize. It can turn solid, not like rock, not like ice, but like diamond. A lattice of carbon atoms locked into place by quantum forces, forming the largest gemstone the universe has ever made. A star in its final act becomes a jewel. For decades, this was just a theory, a mathematical prediction based on physics. Scientists knew that as white dwarfs cooled, the ions in their cores would eventually stop moving so rapidly. They knew that when thermal energy dropped low enough, electrostatic forces would arrange those ions into a crystal lattice. It made sense on paper, but no one had observed it. No one had proof. Then, in 2019, everything changed. Astronomers studying data from the Gaia Space Telescope noticed something strange. They were looking at white dwarfs in our galaxy, measuring their brightness and temperatures when they found a pattern. Some white dwarfs were cooling more slowly than expected, not by much, just a small delay. But it was consistent, it was measurable, and it needed an explanation. The answer, they concluded, was crystallization. When the core of a white dwarf crystallizes, it releases latent heat. The same way water releases heat when it freezes into ice carbon, and oxygen release heat when they lock into a crystal structure. That heat slows the cooling process. It makes the white dwarf slightly warmer, slightly brighter than it would otherwise be. This was the first observational evidence that white dwarfs crystallize. Not a theory anymore, not speculation, proof, hidden in the light curves of distant stars. The discovery was published in the journal Nature, and it confirmed what physicists had suspected for nearly 50 years. White dwarfs don't just fade away, they transform. They become something fundamentally different, something solid, something ordered, something that defies the chaos of their birth. Imagine that. A star that once burned with nuclear fire, that fused hydrogen into helium and helium into carbon and oxygen, now cooling so slowly that its core solidifies. The same carbon that exists in every living thing on Earth, now locked into a crystal lattice the size of a planet. A diamond bigger than mountains, bigger than continents, bigger than worlds. And it's not just carbon. Some white dwarfs crystallize oxygen as well. The exact composition depends on the mass and history of the star. Lower mass white dwarfs have more carbon. Higher mass white dwarfs have more oxygen. But in both cases, as they cool, the core transitions from a liquid-like plasma into a solid crystalline structure. It's a phase change, like water turning to ice, like vapor condensing into liquid, except it's happening inside a star under pressures and densities we can barely imagine at temperatures that would vaporize anything on Earth. Scientists estimate that crystallization begins when the temperature in the core drops to around 10 million Kelvin. That's still unimaginably hot by human standards, but it's cool enough for the ions to start settling into place. The process doesn't happen all at once. It starts at the center where the density is highest and slowly works its way outward. Over billions of years, more and more of the core solidifies. The white dwarf becomes layer by layer a crystal. One of the white dwarfs suspected to be heavily crystallized is BPM 37093, located about 50 light-years from Earth in the constellation Centaurus. Astronomers have nicknamed it Lucy after the Beatles' song Lucy in the Sky with Diamonds. Based on its temperature and mass, scientists believe that a significant portion of its core has already crystallized into carbon. It's not entirely solid yet, but it's getting there. Slowly, patiently, one atomic layer at a time. BPM 37093 has a mass of about 1.1 times that of our Sun, packed into a sphere roughly the size of Earth. Its surface temperature is around 12,000 Kelvin, which means it's been cooling for billions of years. And inside, hidden from view, protected by layers of degenerate electrons, there's a core of crystallized carbon. A cosmic diamond drifting silently through space. Here's a question worth considering. What does it mean for something to be a diamond if no one can ever touch it? If no one can ever see it? If it exists only as a prediction, a model, a conclusion drawn from spectra and light curves? In a way, it doesn't matter. The diamond is real whether we see it or not. The crystallization happens whether we observe it or not. The universe doesn't care about our ability to witness. It just follows its rules. Temperature drops, ions slow, structure emerges. That's enough. But there's something poetic about it, isn't there? The idea that deep inside dying stars, there are treasures beyond imagination. Gems the size of planets. Crystals formed not by pressure from above, but by the slow, patient cooling of matter over eons. Diamonds that will never be mined, never be worn, never be valued by anyone except the scientists who inferred their existence. People often misunderstand what we mean by diamond in this context. They imagine something shiny and transparent like a jewel in a ring. But the crystals inside white dwarfs aren't like that. They're not gemstones, they're atomic lattices. Carbon atoms arranged in a repeating pattern, each one locked in place by electromagnetic forces. There's no light passing through, no sparkle, no shine, just structure, just order. And yet, in a deeper sense, they are diamonds. The arrangement of atoms is the same. The bonding is the same. If you could somehow extract a piece of that crystallized core and bring it to room temperature and pressure, it would be diamond, harder than anything on Earth. Denser than anything we've ever created, a fragment of a star turned into stone. The physics of crystallization is fascinating. In normal matter, atoms vibrate, they move, they have thermal energy. But as temperature drops, that energy decreases, the atoms slow down. And at some point, the attractive forces between them become stronger than their kinetic energy. They lock into place, they form a lattice. They become solid. In a white dwarf, this process is complicated by the extreme density. The ions are already packed incredibly close together, separated only by the pressure of degenerate electrons. But even in that crowded environment, crystallization can occur. The ions find positions where they minimize their energy. They settle into patterns. They build structure from chaos. Scientists have run computer simulations to model this process. They input the temperature, density, and composition of a white dwarf core and let the physics play out. And every time the same thing happens, the ions crystallize. They form a body-centered cubic lattice for carbon or a face-centered cubic lattice for oxygen. The exact structure depends on the element, but the outcome is always the same. Order emerges, crystals form, and when those crystals form, they release heat. Not much, just a small amount of latent energy. But in a white dwarf, where every bit of thermal energy matters, that small amount is enough to slow the cooling, enough to keep the star glowing a little longer, enough to delay the inevitable darkness by millions or even billions of years. This has profound implications for how we understand white dwarf evolution. Before the discovery of crystallization, scientists thought white dwarfs cooled at a steady, predictable rate. Now, we know that's not quite true. There's a phase where crystallization releases extra heat, a plateau, a delay, and that delay changes everything. It changes how we estimate the ages of white dwarfs. It changes how we use them as cosmic clocks. It changes our understanding of the history of the galaxy. Some of the oldest stars in the Milky Way are white dwarfs. They've been cooling for 10 billion years or more. By studying their temperatures and comparing them to models that include crystallization, astronomers can refine their estimates of when those stars formed. And from that, they can infer the age of the star clusters and galaxies they belong to. In a sense, white dwarfs are fossils, not biological fossils, but cosmic ones. They preserve information about the past, about the stars that came before, about the conditions in the early universe. And crystallization is part of that story. It's a chapter in the slow, patient transformation of matter over time. But here's the thing that surprises most people. Crystallization doesn't happen all at once. It's not like flipping a switch. The core doesn't suddenly turn solid. Instead, it crystallizes gradually, starting from the center and spreading outward. At any given moment, part of the core might be solid, while the outer layers are still liquid plasma. Imagine a planet with a solid iron core and a molten mantle. Earth is like that. The inner core is solid, the outer core is liquid, and the mantle is somewhere in between. White dwarfs are similar, except instead of iron and rock, it's carbon and oxygen. And instead of geological time scales, it's cosmological ones. Over billions of years, the crystallization front moves outward. More of the core solidifies. The liquid region shrinks. Eventually, almost the entire white dwarf might be crystallized, with only a thin shell of degenerate matter remaining on the surface. But by that point, the universe will be unimaginably old. Stars like our sun won't exist anymore. Galaxies will have aged beyond recognition. And the white dwarfs will still be there, cooling slowly, crystallizing patiently, drifting through the void. There's a lesson in that persistence, in that slow transformation. White dwarfs don't rush toward their final state. They don't hurry. They just exist moment by moment, atom by atom, building order from disorder, structure from chaos. And in doing so, they remind us that even in death, there's complexity. Even in endings, there's transformation. The fire may be gone, but the chemistry continues. The fusion may have stopped, but the atoms still interact, still arrange, still create something new. That's the hidden chemistry of white dwarfs. Not fusion, not burning, just cooling, just crystallization. Just the slow, inevitable settling of matter into its lowest energy state. And somewhere in that process, beauty emerges. Not beauty we can see, not beauty we can touch, but beauty nonetheless. The beauty of structure, of patterns, of a universe that follows rules even when no one is watching. So when you think of white dwarfs, don't just think of them as dying stars. Think of them as alchemists, turning heat into order, turning chaos into crystals, turning the remnants of fusion into something solid, something lasting, something that will endure long after everything else has faded. But white dwarfs are not always alone. Many of them have companions. And when they do, the story becomes more complicated, more dynamic, more violent. Not all stars die alone. Many are born in pairs circling each other in gravitational embrace, bound together for billions of years. And when one of those stars dies when it sheds its outer layers and becomes a white dwarf, the other remains. Still burning, still alive, still orbiting its quiet companion. This is where the story changes. A white dwarf in isolation will cool peacefully, patiently for trillions of years. But a white dwarf with a companion has options. It can steal, it can accumulate, it can grow. And if it grows too much, if it crosses the line that nature has drawn, it will explode. Not all endings are quiet. Binary star systems are common in the universe. Scientists estimate that more than half of all stars exist in pairs or groups. Two stars orbiting a shared center of mass, held together by gravity, sometimes separated by distances larger than our solar system, sometimes so close they almost touch. When one star in a binary system evolves faster than the other, when it exhausts its fuel and becomes a white dwarf, the system enters a new phase. A phase of interaction, of exchange, of potential violence. The companion star is still burning, still fusing hydrogen in its core, continues to evolve. If it's a main sequence star, it will swell as it ages. If it's already a red giant, its outer layers are loose, extended, vulnerable. And the white dwarf, small and dense with gravity far stronger than its size suggests, begins to pull, not intentionally, not with purpose, just with the simple, relentless mathematics of mass and distance. This process is called mass transfer. Material from the companion star streams toward the white dwarf, pulled by gravity, spiraling inward, forming an accretion disk. The disk glows from friction and heat. The white dwarf feeds, slowly, steadily, growing heavier with each passing year. One of the most famous examples of this is RS Ophiuchi, a binary system about 5,000 light-years from Earth. It consists of a white dwarf and a red giant companion. The red giant is shedding material, and the white dwarf is collecting it. Every few years, enough hydrogen accumulates on the surface of the white dwarf that it ignites in a sudden burst of fusion. The system flares. It brightens by thousands of times. Astronomers call this a nova, not a supernova, just a nova, a smaller explosion, a hiccup, a release of pressure. Then the process starts again. The white dwarf continues to accrete material, the hydrogen builds up, and eventually it ignites again. RS Ophiuchi has erupted multiple times in recorded history in 1898, 1933, 1958, 1967, 1985, 2006, and 2021. Each time it flares bright enough to be visible from Earth with binoculars. Each time it releases energy equivalent to billions of nuclear bombs. And each time the white dwarf survives, it settles back down, it continues to feed. But here's the critical question. What happens if the white dwarf doesn't lose the material, it accretes? What happens if instead of blowing it off in novae, it holds on to it? What happens if it keeps growing, keeps accumulating mass until it approaches the Chandrasekhar limit? The answer is terrifying and beautiful in equal measure. It explodes, completely, catastrophically. A Type Ia supernova, one of the brightest events in the universe. Type Ia supernovae are different from the supernovae that come from massive stars. Those are called Type II, and they happen when a star's core collapses into a neutron star, or black hole. But Type Ia supernovae come from white dwarfs, specifically from white dwarfs that have grown too heavy. When a white dwarf's mass exceeds 1.4 solar masses, electron degeneracy pressure can no longer support it. The star begins to collapse. And in that collapse, something incredible happens. The temperature and pressure spike so rapidly that carbon fusion ignites. Not slowly, not gently, all at once, throughout the entire star. The white dwarf doesn't collapse into a neutron star. It doesn't form a black hole. It simply detonates. Every atom of carbon and oxygen fuses in a runaway chain reaction. The energy released is staggering. For a few weeks, a single exploding white dwarf can outshine an entire galaxy of hundreds of billions of stars. And then, it's gone. Completely. Nothing remains. Not a core, not a remnant, just an expanding shell of gas and radiation spreading outward at thousands of kilometers per second, enriching the interstellar medium with iron, nickel, silicon, and other heavy elements forged in those final moments of fusion. One of the most studied Type Ia supernovae is SN 1572, also known as Tycho's supernova. In 1572, a new star appeared in the constellation Cassiopeia. It was so bright that it was visible during the day. The Danish astronomer Tycho Brahe observed it carefully, recording its brightness and position over several months. He realized that it wasn't a comet or a nearby object. It was a star, a new star. And then slowly, it faded. For centuries, astronomers wondered what caused SN 1572. In the 20th century, using telescopes that could see in X-rays and radio waves, they found the remnant, a bubble of expanding gas still racing outward from the explosion. By analyzing the spectrum of that gas, they determined that it was a type Ia supernova. A white dwarf pushed past the Chandrasekhar limit, obliterated in an instant. Today, the remnant of Tycho's supernova is still visible. It's a shell of hot gas glowing in X-rays, expanding at about 5,000 kilometers per second. And at its center, there's nothing. No neutron star, no black hole, just empty space. The white dwarf that exploded is simply gone. Type Ia supernovae are incredibly important to astronomy, not just because they're spectacular, but because they're consistent. Every type Ia supernova is caused by a white dwarf reaching the Chandrasekhar limit and exploding. And because the physics is the same every time, the brightness is roughly the same every time. This makes them standard candles objects whose intrinsic brightness we know. By measuring how bright they appear from Earth, we can calculate how far away they are. In the 1990s, astronomers used type Ia supernovae to measure the distances to distant galaxies. What they found shocked the world. The universe wasn't just expanding, it was expanding faster and faster. The rate of expansion was accelerating. This discovery led to the concept of dark energy, a mysterious force pushing galaxies apart. And for this work, 3 astronomers, Saul Perlmutter, Brian Schmidt, and Adam Rees, won the Nobel Prize in Physics in 2011. All of that came from studying white dwarfs, from understanding what happens when they explode, from using their destruction as a tool to measure the cosmos. But not all white dwarfs in binary systems explode. Some just keep erupting in novae, shedding the material they accrete before it builds up too much. Others merge with their companions, creating bizarre hybrid objects, or triggering explosions in different ways. The outcomes depend on the masses, the orbital distances, the rates of mass transfer, and 100 other variables. One fascinating system is T Coronae Borealis, located about 3,000 light-years away. It's a recurrent nova similar to RS Ophiuchi. The white dwarf in this system accretes material from a red giant companion, and every 80 years or so, it erupts in a nova. The last eruption was in 1946. The next is expected sometime around 2024 or 2025. Astronomers are watching closely, waiting for the flare. When T Coronae Borealis erupts, it will briefly become visible to the naked eye, appearing as a new star in the constellation Corona Borealis. For a few days, maybe a week, it will shine brightly. Then it will fade, and the cycle will begin again. The white dwarf will continue to feed. The hydrogen will build up, and in another 80 years, it will erupt once more. This is the dance of binary systems, a cycle of accumulation and release, of quiet feeding and violent eruption, of patience interrupted by sudden brilliant chaos. Here's a common misconception. People assume that white dwarfs in binary systems are passive, that they just sit there accepting material from their companions waiting to explode. But that's not quite right. The white dwarf's gravity shapes the system. It pulls on the companion star, distorting its shape, stripping away its outer layers. The accretion disk glows with energy, sometimes outshining the white dwarf itself. And the magnetic field of the white dwarf, if it has one, can channel the inflowing material into narrow streams that slam into the surface at specific points, creating hotspots that rotate with the star. Some white dwarfs in binary systems are incredibly magnetic. Scientists call them magnetic cataclysmic variables. The magnetic field is so strong, millions of times stronger than Earth's, that it locks the accretion disk in place, forcing material to follow the field lines down to the magnetic poles. When the material hits the surface, it releases X-rays and ultraviolet radiation. These systems flicker and pulse as the white dwarf rotates, creating a lighthouse effect, a beacon in the darkness. One such system is AM Hercules, located about 288 light-years away. The white dwarf in this system has a magnetic field of about 230 million Gauss. For comparison, Earth's magnetic field is about half a Gauss. The field is so strong that it completely dominates the system, controlling where and how material falls onto the white dwarf. AM Hercules is the prototype for an entire class of magnetic white dwarfs now called polars. These systems are laboratories for extreme physics. The densities, the magnetic fields, the temperatures, all far beyond anything we can create on Earth. By studying them, scientists learn about matter under conditions that are otherwise inaccessible. They learn how magnetic fields interact with plasma, how accretion works, how explosions are triggered, how the universe behaves at its extremes. But perhaps the most profound lesson from binary white dwarfs is this: context matters. A white dwarf alone is peaceful, patient cooling slowly over trillions of years. But a white dwarf with a companion can be violent, unpredictable, destructive. The same object under different circumstances behaves in completely different ways. And that's true for everything, isn't it? Isolation leads to one fate. Interaction leads to another. Neither is better or worse. They're just different paths, different stories, different endings. So, when you think of white dwarfs, don't just think of them as solitary embers fading in the void. Think of them also as dancers, as thieves, as time bombs, as stars that, given the right circumstances, can still burn bright, can still explode, can still reshape the universe around them. The binary systems remind us that even in death, stars can interact. Even as remnants, they can influence. Even when the fire is gone, they can still ignite. But there's another way white dwarfs interact with the universe. Not through mass transfer, not through explosions, but through gravity, through the bending of space-time itself. And that bending creates something we can detect, even from across the universe. Imagine two white dwarfs circling each other in the darkness. No light passes between them. No material exchanges hands. Just gravity. Just the invisible pull of mass on mass bending the fabric of space-time itself. As they orbit, they create ripples, waves, distortions that spread outward at the speed of light, carrying energy away from the system, pulling the two stars closer together with each passing year. These are gravitational waves, not sound, not light, but vibrations in the structure of reality itself. And white dwarfs in tight binary orbits are among the loudest sources in the universe. Einstein predicted gravitational waves in 1916 as part of his general theory of relativity. He showed that mass doesn't just attract other mass, it curves space-time. And when massive objects accelerate when they orbit or collide or spin, they send ripples through that curvature. Like a stone dropped in a pond, but the pond is the universe, and the ripples are distortions in the very geometry of space and time. For decades, gravitational waves were just mathematics, a prediction, a consequence of equations that seemed too abstract to be real. No one had detected them. No one knew if they truly existed. But in 2015, that changed. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The source was two black holes, each about 30 times the mass of the Sun, spiraling together and merging in a violent collision 1.3 billion light-years away. The discovery was groundbreaking. It confirmed Einstein's prediction. It opened a new way of observing the universe, and it earned the Nobel Prize in Physics in 2017. But LIGO was designed to detect high-frequency gravitational waves, waves from black holes and neutron stars, objects so dense and so violent that their collisions shake space-time in measurable ways. White dwarfs create different waves, quieter, lower in frequency, too faint for LIGO to detect. But they're out there. All across the galaxy binary, white dwarfs are orbiting each other, radiating gravitational waves, slowly spiraling inward, and in the future, we'll be able to hear them. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave detector. Unlike LIGO, which sits on Earth and measures high-frequency waves, LISA will float in space far from Earth's vibrations, measuring low-frequency waves. Waves from white dwarf binaries. Waves from supermassive black holes. Waves from events that happened millions or even billions of years ago, now washing over us like echoes from the deep past. LISA is scheduled to launch in the mid-2030s. When it does, it will detect thousands of white dwarf binaries, maybe tens of thousands. Scientists estimate that the Milky Way contains millions of binary white dwarfs, many of them orbiting so closely that they complete one orbit in minutes or hours. These systems are gravitational wave factories constantly radiating, constantly losing energy, constantly spiraling inward. One of the most remarkable systems astronomers have found is J0651, located about 3,000 light-years from Earth. It consists of two white dwarfs orbiting each other every 12.75 minutes. 12 minutes. That's faster than most people eat lunch. These two dead stars, each about the size of Earth, each containing the mass of the Sun, whip around each other at speeds of hundreds of kilometers per second. The orbital period of J0651 is shrinking. Scientists have measured it. Every year, the two white dwarfs orbit each other about 0.26 milliseconds faster than the year before. That might not sound like much, but it's exactly what general relativity predicts. The system is losing energy to gravitational waves. The waves carry that energy away, and as they do, the orbit decays. The white dwarfs spiral inward, closer and closer. In about 900,000 years, the two white dwarfs in J0651 will collide. What happens then depends on their combined mass. If the total mass is below the Chandrasekhar limit, they'll merge into a single more massive white dwarf. If the total mass exceeds the limit, they'll explode. A type Ia supernova, a flash of light visible across the universe. But for now, they just orbit, silent, invisible to optical telescopes, but screaming in gravitational waves, shaking space-time with every orbit sending ripples outward in all directions, announcing their existence to anyone who knows how to listen. Here's something most people don't realize. Gravitational waves don't just carry energy. They carry information. When LISA detects waves from a binary white dwarf system, it won't just know that the system exists. It will be able to measure the masses of the two white dwarfs, the distance between them, the shape of their orbit, even the orientation of the orbit relative to Earth. All of that information is encoded in the waves, in the frequency, in the amplitude, in the way the signal changes over time. It's like listening to a song and being able to tell not just that a guitar is playing, but what kind of guitar it is, how it's tuned, who's holding it, and where they're standing. Gravitational waves are that precise, that rich, that full of detail. And because gravitational waves travel at the speed of light and pass through matter almost unimpeded, they give us a view of the universe that nothing else can. Light can be blocked by dust, absorbed by gas, scattered by magnetic fields. But gravitational waves just pass through. They don't care about obstacles. They don't interact with matter in the usual ways. They're messages from the universe written in the language of space-time itself. Scientists believe that once LISA is operational, it will detect so many white dwarf binaries that they'll create a background hum, a gravitational wave background. Thousands of systems all radiating at slightly different frequencies, all blending together into a continuous signal. It will be like standing in a forest and hearing the rustling of leaves, not individual leaves, but the collective sound of the whole forest moving in the wind. This background will tell us about the population of white dwarfs in our galaxy. How many there are, how they're distributed, how often they merge. It will be a census, a survey, a map of the dead stars that fill the Milky Way, invisible to our eyes but loud in gravitational waves. One of the strangest things about gravitational waves is how they affect space itself. When a gravitational wave passes through you, it stretches and compresses space in alternating directions. Not much, not in any way you'd feel, but measurably. LIGO detected changes in distance smaller than the width of a proton. That's how sensitive the instruments are. That's how subtle the waves can be. Imagine space-time as a fabric, and gravitational waves as ripples traveling through that fabric. When the ripple passes, the fabric stretches in one direction and compresses in the other. Then it reverses, back and forth, oscillating at the frequency of the wave. For a white dwarf binary, that frequency might be millihertz thousandths of a cycle per second. Slow, gentle, but persistent. And here's the beautiful part. Those ripples are real. They're not just analogies or metaphors. Space actually stretches and compresses. Time actually speeds up and slows down ever so slightly as the wave passes. The universe itself is vibrating, responding to the motion of distant masses carrying messages across billions of light years. There's a philosophical depth to this that's worth pausing on. Gravitational waves mean that nothing in the universe is truly isolated. Every massive object that moves affects the fabric of space-time. And that effect propagates outward forever, touching everything. You can't wall yourself off from gravity. You can't shield against it. It connects everything to everything else. Two white dwarfs orbiting each other in a distant corner of the galaxy are in a very real sense touching us. Their motion creates waves that pass through Earth, through your body, through every atom you're made of. You don't feel it. You don't notice it. But it's happening, right now. Constantly. There's a system called ZTF J1Phen39 Plov5027, one of the shortest period white dwarf binaries known. The two stars orbit each other every 6.91 minutes, not hours, minutes. They're so close that if you could stand on the surface of one, the other would fill half the sky glowing faintly just a few 100,000 kilometers away. Scientists have calculated that ZTF J1Phen39 Plov5027 will merge in about 130,000 years. The gravitational waves are already pulling them together. The orbit is shrinking, and when they finally collide, they'll either merge into a single massive white dwarf, or if the combined mass is too great, explode in a supernova that will briefly outshine the entire galaxy. But until then, they orbit and radiate and shrink, step by step, orbit by orbit, wave by wave. Here's a question. Can you hear? Silence. Not the absence of sound, but the quiet hum beneath it. Gravitational waves are like that. They're not loud. They don't demand attention, but they're there. A constant murmur, a background frequency, the universe breathing. One of the challenges with detecting gravitational waves from white dwarfs is distinguishing individual systems from the background. With so many binaries radiating at similar frequencies, it's hard to pick out a single signal. It's like trying to hear one conversation in a crowded room. Possible, but difficult. Lisa will use a technique called matched filtering, where scientists create models of what a gravitational wave from a specific type of system should look like, then search the data for signals that match. By comparing the observed waves to the predicted waves, they can identify individual sources, measure their properties, and track how they evolve over time. Some white dwarf binaries are so loud that they'll stand out immediately. Others will be hidden in the noise detectable only through careful analysis. But all of them loud or quiet are out there. All of them are radiating. All of them are spiraling inward, slowly, patiently following the inexorable logic of general relativity. There's a kind of poetry in that inevitability. Gravitational waves don't ask permission. They don't negotiate. They just happen. Mass moves, space-time responds, waves spread. It's a law of nature, as fundamental as gravity itself. And white dwarfs with their dense masses and tight orbits are perfect sources. They're lighthouses in the gravitational wave spectrum, beacons that will guide us toward a deeper understanding of the universe, not through light, not through radiation, but through the geometry of space and time. Think about what it means to detect something not by the light it emits, but by the way it bends reality. Not by seeing it, but by feeling the distortions it creates. It's a different kind of observation, a different kind of knowledge. It's like knowing someone is in the room, not because you see them, but because you feel the air move when they walk by. That's what gravitational waves give us, a way to sense the universe through its structure, through the ripples and curves and oscillations in the fabric of existence itself. And white dwarfs, quiet as they are part of that symphony. Every orbit a note, every binary a chord, every merger a crescendo. The universe is singing, and gravitational waves are the song. But even as white dwarfs radiate and spiral and eventually collide, there's another fate waiting for them. A fate so distant, so far in the future, that it stretches the imagination. A fate where even the faintest glow fades completely, and the universe enters a new kind of silence. There will come a time unimaginably far in the future when the last white dwarf finally goes dark. Not dim, not faint, completely dark. No glow, no warmth, no radiation of any kind. Just a cold crystallized sphere drifting through a universe that has grown old and empty and silent. This object, this final form, has a name: Black Dwarf. A star that has cooled so completely that it no longer emits any detectable light. The ultimate end. The last whisper of a fire that burned billions of years ago. But here's the astonishing part. No black dwarf has ever existed. Not one. The universe simply isn't old enough. The universe is about 13.8 billion years old. That sounds like an eternity. But compared to the time it takes for a white dwarf to cool completely, it's nothing. A blink. A moment. Scientists estimate that it takes roughly 10 to the power of 15 years, a quadrillion years, for a white dwarf to cool to the point where it's no longer detectable. That's about 100,000 times longer than the current age of the universe. Think about that scale for a moment. If the universe were a single day old, a quadrillion years would be 200,000 years. If the history of the universe were compressed into a single year, a quadrillion years would span 72 million years. It's a timescale so vast that it defies comprehension. And yet, that's how long white dwarfs can persist. That's how patient they are. So, when we talk about black dwarfs, we're not talking about something that exists now. We're talking about a prediction, a consequence of thermodynamics, a fate that will arrive only in the deep, deep future, long after stars have stopped forming, long after galaxies have dispersed, long after the universe has changed beyond recognition. This future has a name. Scientists call it the heat death of the universe. Not a dramatic ending, not an explosion or collapse, just the slow, inevitable march toward maximum entropy, toward equilibrium, toward a state where no energy flows, no work is done, no change occurs. A universe that has run out of usable energy. A universe that has finally stopped. The concept of heat death comes from the second law of thermodynamics, which states that entropy disorder, randomness. The spreading out of energy always increases in a closed system. The universe, as far as we know, is a closed system. There's nothing outside it to add energy. So over time, energy spreads out. Hot things cool, cold things warm slightly. Gradients disappear, and eventually everything reaches the same temperature, the same state, a kind of cosmic equilibrium. In this far future, there will be no stars, no fusion, no light. The last red dwarfs, the smallest and longest-lived stars, will have exhausted their fuel and become white dwarfs. And those white dwarfs will have cooled into black dwarfs. The galaxies no longer held together by the gravity of living stars will have dispersed. Black holes will have evaporated through Hawking radiation. Particles will have decayed, and all that will remain are cold remnants drifting through an expanding void. But even in that darkness, even in that silence, black dwarfs will exist. They won't be alive, they won't be active, but they'll be there, solid, dense, real. Monuments to a time when the universe was young and bright and full of fire. One of the strangest things about black dwarfs is that they'll still have mass, still have gravity. They won't glow, but they'll curve space-time. If something were to pass nearby, another black dwarf, a wandering planet, a stray particle, it would feel the pull. It would bend its path. The black dwarf wouldn't notice, of course. It wouldn't care. But the interaction would happen. Gravity doesn't need light to function. It doesn't need heat. It just needs mass. And black dwarfs will have plenty of that. A typical black dwarf will contain about as much mass as our sun, packed into a sphere the size of Earth. That mass won't disappear, it won't evaporate. It will just sit there, invisible, patient, waiting for nothing in particular. Here's a question worth considering. What does it mean for something to exist if there's no one to observe it? If the universe has cooled to near absolute zero? If there are no stars, no planets, no life, no observers of any kind? Do black dwarfs still matter? Do they still count as part of reality? The answer, according to physics, is yes. Existence doesn't depend on observation. Black dwarfs will be there whether anyone sees them or not. They'll have mass. They'll occupy space. They'll interact gravitationally with anything nearby. They'll be real in the most fundamental sense. They'll be part of the fabric of the universe. But they won't be interesting. They won't change. They won't evolve. They'll just exist. Silent. Still, unchanging, for time scales that make the current age of the universe look like a flash of lightning. Scientists have tried to imagine what this far future will look like. One of the most detailed explorations is a paper titled "A Dying Universe: The Long-Term Fate and Evolution of Astrophysical Objects," published in 1997 by physicists Fred Adams and Gregory Laughlin. In it, they divide the future of the universe into cosmological eras, each defined by the dominant processes happening at that time. We're currently in the stelliferous era, the age of stars. Stars are forming, stars are burning, stars are dying. But this era won't last forever. In about 100 trillion years, star formation will stop. The gas needed to create new stars will be used up or locked in remnants. The universe will enter the degenerate era dominated by white dwarfs, neutron stars, and black holes. During the degenerate era, white dwarfs will slowly cool into black dwarfs. Occasionally, two black dwarfs might collide, briefly flaring back into light. But these events will be rare. Mostly the universe will be dark, cold, quiet. After the degenerate era comes the black hole era, when even white dwarfs and black dwarfs are uncommon, and the universe is dominated by black holes. But black holes don't last forever. Through a process called Hawking radiation, they slowly evaporate, releasing particles and energy over time scales of 10 to the power of 100 years or more. And after the black holes are gone, the universe enters the dark era. No stars, no black holes, no light, just particles spreading out, moving apart, drifting through an ever-expanding void. Black dwarfs, if any still exist, will be among the last remnants of structure, the last solid objects, the last things that were once stars. It's a bleak picture, but there's something oddly comforting about it too. Even at the end, even when everything else has faded, some things remain. Not forever. Nothing lasts forever, but for a very, very long time. There's a concept in cosmology called the Big Freeze, another name for the heat death. It's the idea that the universe will expand forever, growing colder and more diffuse until all the energy is spread out so thinly that nothing can happen anymore. No reactions, no interactions, just particles separated by vast distances moving slower and slower as the universe cools toward absolute zero. In this scenario, black dwarfs will eventually reach a temperature of just a few degrees above absolute zero. They won't be emitting any radiation. They won't be glowing in infrared or radio or any detectable wavelength. They'll be thermally indistinguishable from the cosmic background, invisible, silent, forgotten, but they'll still be there, still solid, still crystalline, still holding the memory of a star that burned trillions of years ago. Here's a common misconception. People assume that black dwarfs are black holes. They're not. Black holes are regions of space-time where gravity is so strong that not even light can escape. Black dwarfs are just cold white dwarfs. They still have a surface, they still have a finite density. You could in theory land on one. You couldn't land on a black hole. The distinction matters. Another misconception is that black dwarfs will somehow collapse further, that gravity will win and they'll shrink into nothingness. But that's not what happens. Electron degeneracy pressure doesn't depend on temperature. It's a quantum effect, not a thermal one. Even when a white dwarf cools to absolute zero, the electrons still resist being compressed. The pressure remains, the structure holds, so black dwarfs won't collapse. They won't evaporate. They'll just sit there for eons, for time scales that make 1 trillion years seem brief. There's a strange kind of poetry in that persistence, in the idea that even when the universe has grown old and dark, even when all the light has faded, some things endure. Not because they're trying to, not because they have a purpose, but because the laws of physics say they can't do anything else. Black dwarfs are the ultimate expression of inertia, of existence without change, of being without becoming. They are, in a sense, the final word on what it means for something to last. And yet, even black dwarfs might not be truly eternal. In the unimaginably distant future, 10 to the power of 1,500 years or more, quantum tunneling might cause the protons in a black dwarf to decay. The atoms themselves might disintegrate. The structure might slowly, particle by particle, dissolve into radiation and exotic particles. But that's so far in the future, so beyond the realm of current observation, that it's more speculation than science. For all practical purposes, black dwarfs are the end, the final state, the last thing that was once a star. Do you ever think about endings? Not just personal endings, but cosmic ones. The idea that everything, no matter how vast or bright or important, eventually fades. There's a melancholy in that thought, but also a kind of peace. Endings are natural, inevitable, part of the structure of time itself. White dwarfs cooling into black dwarfs is the slowest, gentlest ending imaginable. No violence, no drama, just the patient dissipation of heat. Just entropy doing what entropy does. It's almost meditative, almost calming. And in that calm and that slow fade, there's a lesson. Change is gradual. Endings take time. Even when the fire is gone, even when the light has faded, something remains. For a long time. Longer than you'd think possible. That's what black dwarfs teach us. Not that everything ends, we already knew that. But that endings can take so long, be so gradual, that they almost don't feel like endings at all. Just transitions. Just the slow passage from one state to another. The universe, it seems, has all the time in the world. And so do white dwarfs. They'll cool, they'll darken, they'll become black dwarfs. And they'll drift through the void, silent and still, until the universe itself forgets they were ever stars. But before that final darkness, before the heat death, before the long silence, there's still light, still warmth, still the faint glow of white dwarfs scattered across the galaxy, cooling slowly, patiently, refusing to disappear completely. And in that refusal and that persistence, there's something worth remembering. We've traveled far tonight. From the moment a star learns to whisper through the collapse that births a white dwarf across the quiet glow of light, without fire into the hidden crystals forming in their cores. We've watched them dance in binary systems, felt the gravitational waves they send, rippling through space-time, and glimpsed the distant future where they fade into black dwarfs in a cooling universe. But now, as we near the end of this journey, let's return to something simpler, something closer. The meaning hidden in all of this, the lesson that white dwarfs, patient and quiet as they are, have been teaching us all along. White dwarfs are not failures. They're not the sad remnants of stars that couldn't make it. They're survivors. They're the natural conclusion of a life well lived, a fire well burned. And in their survival, in their refusal to simply vanish, they show us something profound about the nature of existence itself. Here's the truth that white dwarfs carry. Endings don't erase what came before. When a star becomes a white dwarf, it doesn't forget the billions of years it spent fusing hydrogen-warming planets, creating the conditions for life. All of that history is still there, compressed into its core, radiating slowly into space as heat. The white dwarf is the memory of the star, the living proof that it existed, that it mattered. And that memory doesn't fade quickly. It can last for trillions of years, longer than civilizations, longer than species, longer than continents or oceans or mountains. A white dwarf will outlast nearly everything we can imagine. It will glow faintly in the darkness, long after the Earth is gone, long after the sun itself has become a white dwarf, long after humanity, if we still exist, has spread to the stars or disappeared entirely. There's a humility in that, a reminder that we are brief, that our moments, precious as they are just flickers against the backdrop of cosmic time. But there's also hope, because if a white dwarf can persist for trillions of years, radiating the warmth of a fire that long ago went out, then maybe the things we do, the warmth we give, the light we create can linger too. Not forever, nothing lasts forever, but longer than we think, longer than we dare to hope. Scientists have discovered white dwarfs that are among the oldest objects in the universe. Stars that died when the Milky Way was still young, when the first galaxies were just beginning to form, when the universe was a fraction of its current age. These ancient white dwarfs are still glowing. Faintly, almost invisibly, but measurably. They're still there. One such white dwarf is SDSS J10217 of 48121315.4, a name that sounds more like a password than a star. It's located about 90 light-years from Earth, and scientists estimate it's roughly 11 billion years old. It has cooled to a surface temperature of around 3,900 Kelvin, barely warmer than some red dwarfs. But it still glows, it still radiates, it still exists. When astronomers look at white dwarfs like this, they're not just seeing a cold star. They're seeing a time capsule, a record of the early universe, a witness to billions of years of cosmic history. Every photon that escapes from its surface carries information about the conditions in which it formed, the elements it contains, the processes that shaped it. And in studying these ancient white dwarfs, scientists learn not just about stars, but about time itself. About how matter evolves, about how structure persists, about how the universe, chaotic and violent as it can be, still follows rules, still creates order, still allows things to last. There's a beautiful parallel here between white dwarfs and human memory. Memories fade, yes. They blur and change and sometimes disappear. But some memories persist. They stay with us warm and faint like the glow of a white dwarf. They remind us of who we were, what we experienced, what mattered. And even when the details fade, even when the brightness dims, the memory remains. Real, present, part of us. White dwarfs are cosmic memories. They're what remains when the story is over, but the meaning hasn't faded yet. When the flame is gone, but the warmth still lingers. When the light has stopped being created, but hasn't stopped being seen. And maybe that's the most important lesson of all. That light doesn't need to be bright to matter. That warmth doesn't need to be intense to comfort. That existence doesn't need to be dramatic to be meaningful. White dwarfs teach us patience. They teach us that slow change is still change. That cooling isn't the same as disappearing. That even when everything seems to be winding down, there's still something happening. Still photons escaping into space. Still gravitational waves rippling outward, still atoms crystallizing in the dark. They teach us that the universe is not in a hurry, that time is vast, That endings can take so long they blur into something else entirely. Not quite life, not quite death, just existence, just persistence, just the slow, quiet refusal to be completely gone. Do you ever feel like you're fading, like your brightest days are behind you? Like the fire you once had is cooling, dimming, slipping away? White dwarfs would tell you, that's okay. That cooling is natural. That dimming doesn't mean you're done. You're just changing, transforming, becoming something quieter maybe, but no less real. And here's the thing, even when you think you're dark, even when you think there's nothing left to give, you're still radiating, still affecting the space around you, still bending reality, even if just a little, still here, still mattering. White dwarfs don't try to be bright. They don't fight against the cooling. They just exist, moment by moment, photon by photon, following the laws of physics wherever they lead. And in that acceptance, in that surrender to the natural flow of time, there's a kind of grace. We started this journey with a question: what happens when light learns to rest? And now we have an answer. It doesn't disappear. It doesn't vanish. It just becomes quieter, gentler, more patient. It radiates what it is, asks for nothing in return, and slowly over eons fades into the background of the universe. But it doesn't go quickly. It doesn't rush. It takes its time. Trillions of years, quadrillions, an eternity by any human measure. And in that time, it continues to be light, continues to warm the void however faintly, continues to exist. That's what white dwarfs are: light that has learned to rest, fire that has learned to remember, stars that have learned to let go of burning and discovered that they can still glow. And maybe in our own small ways we can learn from that. We can learn to let go of the need to burn bright all the time. We can learn to value the quiet glow, the faint warmth, the gentle persistence. We can learn that endings are not failures, that cooling is not the same as dying, that even when the fire is gone, we can still be warm. White dwarfs are scattered across the galaxy. Millions of them, maybe billions. Each one glowing softly in the darkness. Each one a testament to a star that lived burned and became something quieter, something lasting. And when you look up at the night sky, remember some of those stars are already white dwarfs, already cooling, already glowing on borrowed light. And they'll keep glowing long after we're gone, long after the sun becomes a white dwarf itself, long after the galaxy has aged and changed and moved on. They're patient, they're persistent, they're proof that even when the universe seems to be winding down, even when entropy increases and heat spreads and order dissolves, some things last. Not forever, but long enough to matter, long enough to be remembered, long enough to glow. So rest easy tonight knowing that the universe is full of quiet lights, stars that have stopped burning but haven't stopped shining, embers that refuse to go dark, memories that refuse to fade. And know that you too can glow without burning, can warm without fire, can exist gently and patiently in the spaces between brightness and darkness. The white dwarfs are still out there, still cooling, still glowing, still waiting. And they'll be there long after this moment has passed, long after this night has ended, long after everything we know has changed. They're not trying to teach us. They're just being what they are. But in being what they are, they show us something beautiful, something true, something worth carrying with us as we drift toward our own rest. Light doesn't need to shout. Warmth doesn't need to blaze. Existence doesn't need to be loud to be real. Sometimes the quietest things last the longest. Sometimes the faintest glow is the most enduring. Sometimes learning to rest is the greatest act of persistence. White dwarfs know this. And now, so do you. Thank you for drifting with me tonight through this quiet corner of the cosmos. Thank you for listening to the story of stars that learn to whisper to glow, without burning to persist, without demanding. These remnants of fire teach us that endings can be gentle, that memory can be warm, and that light once kindled lingers far longer than we imagine. There are countless more stories waiting in the darkness, more whispers from the universe, more quiet wonders to explore. And I hope you'll join me again as we drift together through the next chapter of this endless, beautiful cosmos. Until then, rest well. Let the quiet settle around you. Let the weight of the day ease. And remember that somewhere out in the vast darkness between stars, a white dwarf is glowing just for you. Just because it can, just because it refuses quietly and patiently to let the light go out completely. Sleep well. Dream gently. Good night.